Okay, in this video I promise I'm going to share with all of you our complete versions of our module 2. And what we're going to look next, previously you already do a recap for your fixed number, for the integer representation and also integer arithmetic. Now you're going to look into floating number in terms of the point representation and also arithmetic equation. Lastly, the conclusion. So from your fixed number or your integer number, you learn on the representation, and you also take a look into the arithmetic. Now you go for the floating point numbers. You need to learn on representation and also arithmetic. So similar to that's to the integer and also fixed numbers. What we're going to look, which is representation, component, normalized and unnormalized, format, a simple format, and another one is IEEE 754. What is these two format? Later we will see. Okay, now let's take a look into the first thing first. You can see basically it is mentioned and talk about what is the floating point and why you need to apply this floating point in our real mathematics. We can try to read it. Okay, in terms of representation, floating point, you know already, it is a nombor perpuluhan. Nombor perpuluhan, sometimes you always like use it in your day-to-day activities. It is like very common for you to meet the floating point numbers also. And how basically floating point number allow this decimal place to the right of the decimal point where you put the floating point, which is on the right side. If let's say you have 197, this is your fixed number or your integer. So this is your integer and also fixed number. But when you have the floating point or your radix point ataupun perpuluhan, on the right is going to be your floating point number here. So you have like these normal integer numbers, your fixed numbers, and after this you can see you have the perpuluhan here, which is your radix points, and this is your floating point number. And often we normally also use in terms of scientific notification, we play around with this term, like we have 125, we can also represent it to be 1.25 multiplied with 10 to the power of 2. This is basically similar value. And if we have 0.125, if we want to represent in terms of scientific notification, we can have 1.25 multiplied with 10 to the power of 1, or maybe we can also have 12.5 multiplied with 10 to the power of minus 2, and etc. So it is depend on you how you apply the power here and the value you convert into the scientific notification. But this one, it is not critical because you meet it in your day-to-day activities. But the things what you need to know is first thing, in the plotting point, you need to know the components. First, of course, you're going to have sign. This one you also already looked into in the digital logic subject, your sign number. Okay, then you can see for the signs you have whether it is a positive or also negative number. Okay, so for this one, You can see also we have example decimal number, binary number. You have another base numbers like octal, hexadecimal, and etc. Right? But this one all you can see we normally apply and use decimal and binary. For decimal, we use in our day-to-day life, and for binary, we need to learn it because we are always apply and also meet the computer every single day, and computer only understand the 1010 value. Okay, now first you have a sign. Second, you're going to have significant of fraction and mantissa. Where is it? This is the value of your significant of fractions number here, and the total of mantissa. And after this, you can see also you have the base or the radix. You can see this is your base number, decimal is base 10 or the radix, and this one is your base 2. After this, you have another one, which is your exponent. This is your exponent. So now all together in one, in terms of one numbering, you can have a sign, you can have the significant of fraction or mantissa, you can also have the base or radix, and lastly your exponent. So from all of these, sometimes you got, sometimes you don't have. It depends on the numbers that provide you. In terms of like previous years or previous semester, what type of question? Sometimes they just ask you, give you the numbers, and then they ask what is the mantissa for this number, so you know, okay, this is your mantissa value. What is your best value, that you know, okay, this is the best already point. What is your exponent, so you know, okay, this is your exponent. Okay, so step by step we're going to go deeper and deeper. Okay, if you have any question you did not understand, you can like direct WhatsApp me. Okay, fraction or exponent under here, which is our part, you can be also like positive or negative. It's depend on the questions. Okay, next, wait. Okay, now we're going to move to another subsection, which is we're going to look into the normalized and unnormalized. What is the meaning by normalized and what is the unnormalized? It is very simple, which is for a number which is normalized, you're going to have the numbers after your radix point is non-zero. So let's say you can see this example. Okay, this is unnormalized. For normalized, okay, this is normalized. After your radix point, the number is not zero. Nombor tu bukan zero after your punya nombor perpuluhan. Okay, so that's why it is normalized. But for unnormalized, floating number, after your radix point, it is a zero. So you look into the first number here, 1 point. After you punya nombor perpuluhan, after your radic point, you have 0. Then you meet this scenario, it is unnormalized. So for this number, you have the normalized. And you can see after your radic point, you have 0. Mean it's unnormalized. For this question, after your radic point or after you punya nombor perpuluhan, you have 1 here, so it is not 0. That's why you call it as normalized. Okay, how if let's say you were given with numbers that unnormalized? What you need to do if the number is unnormalized? So you need to normalize it. So there is a process for you to normalization to you to convert from unnormalized to normalized numbers. Normalization is the process of deleting the zeros until non-zeros value is detected. Example, in this question, you were given with 0.00743 times 10 to the power of 4. Okay, let's say I move to, here I can see, after my radic point is 0, then it's unnormalized. So I'm going to make it normalized. How I'm going to make it normalized? I need to move my radic point to the right. I put here, this is 1 time. After my radic point is still 0. I move another 1 time. Then I put my radic points here. So another 1 time, put another point here. Okay, after this, after my radic point is going to be 0.7, which is non-zero. It's normalized now. How many times I move my radic point to the right? If I move to the right, it is a normal mathematic, so we're going to minus 2 times. If you move to the right 2 times, if you move to the left 2 times, we're going to add 2. Later we see the example for this, okay? For now, you can see you have 2 times, 1, 2, to the right. Ya Allah, tak nampak. To the right, you're going to minus 2 times. Okay, where you going to apply this minus 2 times, which is over here at your exponent here, minus 2. So then you will get 0.7 because your normalized number will be like this, 4, 3 times 10 to the power 2. So how you get this? Let's see the example here. We have normalization 2 times. We meet the non-zero here and it's already normalized, and 2 times we're going to minus 2. Then we get the answer for normalized number. And you can see over here there is another example. This is moved to the right 2 times, you're going to minus 2. This is mathematical only. And if let's say you have 45.09, how are you going to make it normalized? First, you need to know that the beginning of number need to be a 0, right? But after your radic point, you can see over here, this is 0. It's mean unnormalized. And in front of you still got number. That's why you need to move to the left. Because just now, for the first example here, your left is all 0. That's why it doesn't matter for you to move to the left. It is a similar value, isn't it? So that's why you need to move to the right as long as in front of you will be 0. So you need to move 1 time, 2 times until you meet after your ready from point to the left is going to be 0. 2 times to the left, you're going to get 0.4509 times 10 to the power of the question starting from 4. To the right, to the left, you're going to add 2. Your final answer will be 10 to the power of 6. Okay, now you can see here there is a rules. You can see a rules of thumb. This one, as I mentioned, is your normal mathematical things, which is when you apply this in your mathematical, you know already, okay, you need to move to the left, you need to move to the right, and etc. Now, what is our first ready point rules of thumb? So you can see, first of all, move ready point to the right, you need to subtract the exponent. Move to the left, you're going to add the exponent. So the one that I teach you just now. Okay, next, there is another example. You can see here, you have this number. Oh, I already mentioned you need to start from 0 point something, but after your ready point, you need to also have a number non-zero. So how to make it? This one, you need to move to the left until you reach 0 in front and there is a ready point. How many times you move to the left? 1, 2, 3. 3 times means that to the left you're going to add your exponent. So the answer is similar over here. Second, you can also apply the similar thing to your binary. But in terms of your binary, you can see here, you have this number and you need to normalize it because this is unnormalized number. You need to put 0 in front and 0, 1, 2. 2 times after your ready point is non-zero and in front is 0, then it is a normalized. For this number normalizations, you can see you move to the 1, 2. 2 times to the left means plus with 2. Okay. For this question, it is written out in binary. Don't forget about binary. So you put all the value here in that binary. You can like convert it to see it. But later on, you can see when you have this number, of course, adding with 2 is also referred to 0, 0, 1, 0. If let's say it is 4-bit. 1, 0 is equal to 2 in the decimal. Check back your numbering system. I hope that you still remember your numbering system. That's why you add 0, 1, 0. Why it is 1, 0? Because if you just use your calculator, you convert decimal to, you convert to binary, your decimal number 2, you convert to your binary, you will get 1, 0. It is not 10, okay? It is not 10. It is a 1, 0 in binary. Base 2, this one is base 10. Now we have another example, another binary example. Over here we have 0 in front. That's why we need to move to the right until we meet. Okay, this one is 0 in front. It's correct. But after your ready point, it is a 0. So you need to move until you find the non-zero. 1, 2, 3. You meet the non-zero after your radic point. 3 times to the right, you're going to minus. Divide it, which is minus, with 3. You can see it's just represent, it's using decimal, but it's also correct if you want to like apply it like to the power of 1001 using the binary, and then you minus with 3 times. What is your 3? 0, 1, 1. Then you will get your answer, which is 6 to the power of, let's say you have 1, 1, 0, 4, 6. Okay, it is very easy for the normalized and unnormalized part. In terms of a test, I guess so, you will also have the possibility to be asked in terms of normalization. You need to normalize the given numbers. Next, let's take a look into the next section. We have over here the format a simple model. So for simple model here, you can see we have a simple model for our binary form. This one, you use it in your normal form, but you're not going to be asked, I think so, in your test or final exam, because we rarely use this. But if let's say they ask you in terms of a simple model, you need to remember this component, which is for simple model. We have sign bit 1 here, and then after that we have exponent, and then we have another sign bit here, and we have the fragment or mantissa, and also significant at this point. So altogether, you need to know the binary format for a simple model. But it's it's very rare for you to apply, because normally we didn't apply this term for a simple model, because it's very hard for us to apply two sign in one format numbers. Okay, but it's okay, you still need to learn a simple model. This is the normalized floating point standard. You're going to have 0 in front, and then point, and this one is your radic point, and then the fraction number. You kena ada nombor kosong di depan dulu, and nombor perpuluhan, and the rest will be your nombor perpuluhan, which is your fraction number. After that, you have base U. If your question is base 10, you put base 10. If your question is base 2, it is base 2. And in terms of exponent, it depends also in question. Sometimes they put directly decimal number like 10 to the power of 10, or maybe it shows you in terms of exponent 1, 0, 0, 1. So this one is 9. And if it didn't show you positive, you need to know it is a positive exponent. Otherwise, for negative, of course it is a negative, right? Negative, you cannot make assumptions to have no negative in front. But the positive, if there is no positive or any sign, it is a positive number. Okay, let's take a look into this format. You can see this two sign bit are not good for design. You can see. That's why I mentioned to you, it is not good for design, as it's incur extra cost. So we need a new representation. That's why I mentioned rarely we will ask you, but in terms of format, if let's say someone asks you, or maybe there is like a question, format for a simple model, format only. Okay, in terms of format, you know the format is look like this, but to apply to the like your real number to be in the format, it is rarely happen because it's going to have extra cost, and we have new improvement for the binary form representation. Okay, now this is an example. If let's say you have a 14 bits model for floating point format. Okay, wait. I heard something. Okay. Now, let's take a look into this example. In this picture, you can see it is an example for 14 bits model. You have the floating point format. Over here, we have 1 bit and 5 bit. You can see 1 bit for sign and 5 bit for exponent, and another one more thing is your significant, and then also it can be a fraction number or a mantissa. So this is new format which is called as 14-bit model for floating point format. Improvement from the simple model. But later on also you're going to have IEEE 754 floating format. Okay, next it's mentioned here, the next few example and exercise, we will use this simple model before we discuss on the IEEE 754 floating format standard. So this is the simple model that we have converted from this format, convert it to be a simple one sign here. And if for the 14 bits, we're going to do like this: 1 bit, 5 bits for exponent, and 8 bits for the significant and mantissa. Let's take a look into the example. First, we have store the decimal number 17 in this model. Okay, we in this model, what is model? I think it is not complete in the model for floating point format, which is a simple model. Okay, now in the simple format, you need to store 17 in binary. Let's convert it. You can like easily convert it using your calculator, but let's try to convert in terms of what I can see over here. We have wait, where is my eraser? Okay, let's try to convert it from our decimal to binary manually. So what is the answer for our binary number? Because we want to apply the simple model for binary, right? Okay, now we have 17 to the power of 0 to the power of 1. If you still remember, I hope you still remember. 16, okay. I have here to the power of 0 is 1, to the power of 1 is 2, to the power of 4, to the power of 2 is 4, to the power of 3 is 8, and to the power of 4 is 16. So I have all together is 14. That's why I'm going to have 1, 0, 0, 0, 1. Why? I'm going to get 16 plus 0 plus 0 plus 0 plus 1 equivalent to 17 in decimal. So please try to remember how to convert. Okay, this is my numbers, which is I have 1 0 0 0 1 binary. I'm going to convert it to normalized numbers. This is unnormalized because what? Your number having this floating point or radix point here, nombor perpuluhan ni, titik perpuluhan is di sini. This is not in front here, but this is here, which is 0 0 0 after this. Okay, because your radix point is here, you need to move until your left side is a 0, right? The left side is 0, and after your radix point is going to be non-zero. So let's take a look. I have moved it 1 2 3 4 5. This one I'm going to get 0 in front, and there is no other value rather than 0, and after my radix point will be 1. So this is in terms of normalized number. I got 0 dot 1 0. Why is slow? 0 0 0 1. Okay, after this you can see you have moved from 1 2 3 4 5 to the left. That's why your starting number, it is like multiply with to the power of 0. Why 0? Kenapa pen I lambat sangat ni? Okay, for the first time when you convert 17, tak boleh, 17 to the binary, you will get 1 0 0 0 1. And check back your standard form, which is this slide. You need to have sign, you need to have your value, you need to have your base, you need to have your exponent, the components here. That's why you're going to do it as positive here. I have the mantissa and the value here, and I'm going to multiply with what? 2, because our base is 2, and the exponent will be 0. When I move to the left, what happened? I'm going to get 0.100001 multiply with 2 the power of 0, add with 5, because it is 5 times. 5 times to the left. Your answer, your final answer will be 0.10001 multiply with 2 the power of 5 for your normalized number. This is your normalized number. I don't know why my pen is very slow. And from this normalized, what you're going to do, you need to convert it into your simple model. If you still remember, for your simple model, you're going to have 1 bit for the sign, 5 bit for the exponent, and 8 bit for the significance of fraction. Let's take a look. What is the bit? Sign. Remember back from your digital logic subject or previous our subtopic, we have sign. If we have 0, it's referred to positive. Positive. Sorry, I don't know. It's very slow. The positive. If 1, it represent as negative. So that's why in our number we have positive here. So our answer we will put, where is, okay, we have 1 bit for our, nak nangis saya macam ni slownya. 1 bit for our sign, and it will be 0. Why 0? Because it's a positive. And after that we have 5 bit for our exponent. What is our exponent? Our exponent is value of 5. When we want to convert 5 to binary, we will get 1, 0, 1. This is your conversions from decimal to binary. But you can see you have 5 bits for your exponent. You have a rules of thumb. What is the rule? For exponent, the exponent is always padding to the left. It's always padding to the left, your exponent number. So for this part, you're going to apply 1, 0, 1. Slowly. 1, 0, 1 for your exponent number equivalent to 5, and you always padding to the left. I sebut right ya? To the left. So you're going to padding and add another 0, 0 at your left side. So this is 5 bits. But vice versa for the rules under a fraction. So it's better for me to charge. It's getting slow. Wait, Okay, you can see over here, rules number 2. For a fraction, you always padding to the right. When you want to padding to the right, what happen? First thing you need to know the answer for a fraction, which is, this is your value. You got 1, 0, 0, 0, 1. And for this part, you have 1, 2, 3, 4, 5. It is only 5 bit. There is a rules, you need to always padding to the right. So you need to complete another 3 bits. The total of 8 bit. We need to padding to the right. Kenapalah macam habis tak buat ni. So that's why you will padding to the right over here. So let's see proper way. You can see first of all, you need to do a unnormalized binary number to a normalized binary. From 17, you convert to the binary, you will get 1, 0, 0, 0, 1. 0.0 multiply with 2 to the power of 0. You need to normalize it. You need to move to the left until you find the 0 and on the left side and non-zero to the right. And you will get this answer for the normalized. And this is your fraction, this is your exponent, this is your base, and in front is your sign. Sign will be a positive, it's going to be a 0. And for the exponent part, you have 5 bits, but your answer only have 3 bits. You need to padding to the left, you add another 0, 0 on the left side. While for your number, for your significance of fractions number, what you need to do is you need to have 8 bits. But there is a rule for fraction, you need to always padding to the right. That's why you need to add another 0, 0, 0 at your right side. Okay, so it's very easy, this example. Please try play around with another numbers and apply it into the solution. Okay, the another example for exercise 2.7. You can try it. You were given with this number. What you need to do, you need to convert it into a binary. After you convert to binary, you need to do the normalization. When you done the normalization, you can directly convert to your sign. So you need to show your working step by step similar to this one. Try to convert it. You can just simply using your calculator. Okay, you will find another format. Just now is a simple model for your floating point format. But now there is another format which is called as Bias Exponent. So in question, sometimes you can be said, okay, write the decimal number blah 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 in floating point represent in the exponent bias exponent representation or bias exponent format. So you need to use this format later on that we will learn. But if let's say in question is mentioned to, okay, use the floating point representation, the one that's a simple model you just learned, so you apply this. And sometimes there is another one which is use the IEEE representation format. So after this bias exponent, we will learn on the IEEE standard. It's mentioned here, this is used, which is bias exponent will be used unless IEEE standard is mentioned. Then it's the different calculation. But normally in question, we will help our student. We will directly inform what format we need you to use. Okay. So no worry. One obvious problem with this model is negative exponent cannot be representation for the bias exponent. Sorry. We have a negative exponent. You can see over here. Where is it? Okay. For this part, for our floating point representation, the simple model, if we have numbers here positive, it's okay for the exponent. But when you have like -3, -2, -1, you cannot, and it's hard for you to represent in terms of your format here. So that's why we have the solution. Negative exponent cannot represent, right? So that's why this is our solution, which is using a bias exponent. It's mentioned bias exponents because you have the problem with the previous format. You cannot represent the negative. So for bias exponent here, it is similar. You have the sign 1 bit. Normally it's going to be only 1. Why? Because you have positive to be 0, negative to be 1. Only these possibilities. There is no like positive negative in one numbers. So you need to have either one, whether it is positive or it is a negative. Next, we have the, instead of exponent last time, we have the bias exponent. with the n bits. So n bits is a bits of exponent format. So we will need to check the bits of the exponents that this question is given. And lastly, the value of your significance or your fraction. Last time it's give you here is 5 bits and here is at bits right. So let's take a look into the bias exponent, what will happen. And in our bias exponent, there is several equations you need to memorize. First of all, you need to know what is the units that we'll be using. So you will have EB, which is a bias exponent for this part. This is represented as EB. And N is the bit of your exponent format. To calculate the bias value, which is for your B, the bias value you will have B equal to 2 to the power of n minus 1. So please make sure you remember this format for bias value. Normalized exponent, this is normalized exponent. Let's say you have just now 0.1, okay, for this part, this is unnormalized. So the exponent here is not the answer. So the normalized exponent, which is equal to your E prime. E prime is normalized exponent. Your E prime will be referred to normalized numbers, and this will be your E prime. Let's say you have another example. Let's see another example. Okay, over here, if you have example, okay, just assume this to be binary. Okay, just assume. But if let's say this is your two best whatever number here, okay, you already have like a normalized number. This is your E prime. But for this part, you can see this is unnormalized number, and this is not your E prime, not, because it is unnormalized. So only normalized number you will know, okay, this is your E prime, this is normalized, this is your E prime. So go back to the slide. First, you have this, and you have this equation, how to calculate this bias exponent. Going to have EB equal to E prime, your normalized exponent, plus with your B bias value. Let's take a look what is N here, so then you know the bias value. So the bias value is a number near the middle range of the possible value. Okay, this one is just explanations, but you need to understand it. Typically, the bias value, which is B, is equal to, similar to this equation, equal to 2 to the power of n minus 1, where n is the number of bits in binary exponent. If positive value, any number larger than 2 to the power of n minus 1 in the exponent field, equal to bias exponent plus a bias value plus exponent. If negative value, you will get bias value minus your exponent. So let's take a look into step by step how you're going to get from number, let's say this is your number, how you're going to come out with your bias exponent format. Now you have a similar example last time, which is you got 17. So no need for me to show you how you get this and this value, because this is already been taught in our example number 17. We got already the normalized number. We got the normalized exponent. We got what else? We got the sign. The sign is a positive number. So this is our positive number, which is equal to 0. And then we need to put the this one is the example for just now for your fraction plotting point, which is your simple model. Now you want to convert to your bias exponent. So from here you can see you will use the bias value, which is equivalent to b to the power of n minus 1. What is your n? Your n is the value of your exponent here. What is your exponent here? The bit of your, where is it? N is the bit of the binary exponent. This one, which is 5. You have 5 here, and you got to the power of 4 equal to 16. Then stop, you get the bias value. And from this equation, you also have wait. Okay, from this part you can see you have the bias value already. And the bias exponent, how you get the bias exponent for the part, your format will be sine bias exponent, which is your EB, and another one is your fraction, right? So how you get your bias exponent? You're going to use EB equal to E prime plus B. Where is your E prime? This is your E prime. The B here you get from this equation. That's why you get 21. From 21, you're going to convert it into binary. So that's why you will get this part. Let me check. 0, 1, 2, 3, 4. 4 is 16, plus with your 4 here, you will get 20, plus with 1 here, altogether you will get 21, which is this part. When you convert to binary, you get 0, 1, 1, 0, 1, 0, 1. And for your significant, which is similar to this part, only the difference at the bias exponent at this side. So let's take a look next example. If you have the question with store the decimal number 0.25 in the floating point representation. Oh, this one is your floating point representation, not the bias exponent representation. Floating point representation, you know already, your format will be sine 5 bit for your exponent and 8 bit for your significant and fraction. But here EB, it is a bias exponent format. Okay, now let's take a look the step by step. From this 0.25 5. You need to convert to your binary. The step here is from your digital logic subject. Your numbering system, you need to convert to from decimal, base 10 to binary. You're going to use the repetition multiplication. Please check the notes. But now I'm going to show you. You're going to multiply with whatever base that you want to change with. Okay, from decimal, you want to convert to binary. That's why your your number, fraction number, you're going to multiply with 2. If you want to convert to 8, going to multiply with 8. If you want to convert to 16 base, going to times with 16. But this is repetitions multiplication only for your fraction number, hanya untuk nombor perpuluhan sahaja. Check back your digital logic subject. You will know that repetition multiplication is for nombor perpuluhan. Okay, when you have 0.25, you multiply with 2, you will get 0.5. And repeat. You need to repeat again. You repeat what the value that you will take is only at the fraction number. So you bring here, you will get 0 in front still, which is your fraction number, and 5 multiplied with 2, you will get 1.0. So you continue, bring 0 in front, nothing happen. That's why you will stop. If you still remember in your digital logic subject, you're going to stop until you get 0 at your fraction number. So what is your answer? You're going to take only this part and you will read from top to bottom. Your 0.25 decimal convert to binary, your answer will be 0.01 binary. 0 and 1. Why you put 0? Because you know already this is for your fraction number. Let's say you have any other numbers. We just give you example. I don't know the value. Is it? Okay, I find some things that easy. And okay, for this number, let's say I have 0.3. Can 0.3 get? Okay, you have 0.3 numbers for decimal. You want to convert to binary. You times with 2, what you will get? You're going to get 0.6. And you will bring down this 6 here, which is 0.6. Multiply with 2 again, you will get 1.2, isn't it? So you will only bring the 0.2, not 1. 1 is remain. All in front the radix point, semua nombor di depan daripada nombor perpuluhan ni, you stare it there. You hanya bawa yang belakang saja to repeat with your multiplication. You get another one more time, which is 0.4. You continue again, 0.4 multiply with 2, you will get 0.8. So you repeat again, 0.8 multiply with 2 equal to 1.6. Okay, when you going to stop? Just now there is a scenario, if you meet 0, then you're going to stop. But if it's continuously, it will happen. You can sometimes get continuously. When you're going to stop, it depends on the question. Normally we will put like, okay, please shows the answer in terms of 4 radix point, 4 fraction point. For fraction point, so 4 times, which is over here you have, starting from here, right? You have your answer 0.01001. 0.1001. 1, 2, 3, 4. Oh, until here only, because you want 4 floating point. 4 bit floating point. So that's why you only get 4 times here. So you stop. Sometimes your answer will be repeating. This one I already answered. This one is I already teach you on the numbering system. Okay. I hope you understand. If not, you need to go back, dig your digital logic notes. Okay. After this, you can see this is your answer, which is 0.01 times with 2. Why 2? Because you already get the best 2, the power of 0. And of course, your number will be positive. So from here, you need to do what? Normalization. Over here, you will move to your right. One time, you will see you get, oh, I already get the normalization number. And one time only, what you need to do, you're going to deduct with 1. 0 minus 1, you will get minus 1. So for this part, what you're going to do is you already find the normalization things. You can convert it to your format. But you can see over here, this is normalized. This is the value for E prime. This is the value of E prime. This is the value for your significant of fractions. And you're going to look into the bias if you want to apply into your bias exponent. But for the normal floating point, you can directly apply like 0.0001 for your exponent. And for the significant and fraction, you will get 10000 until 8 bits altogether. And in front will be positive as a 0. 1, 2, 3, 4, 5, 6, 7, 8, 2, 4, 9, 8. Okay. Now let's take a look. This one is, I think the question mentioned supposedly it is a bias exponent, because it's applied into the bias exponent value format. You can see over here you have the bias value of, what is your bias value? B equal to 2 the power of n minus 1. N is what? Your E prime here. Your n here will be your your value here, which is your supposedly it is your normalized value. So you got over here 5 minus 1. Where you get the 5 over here, you need to check back the value of 1 for your n. Where is your n? Go back to your previous slide. Your n is the bias exponent. The binary exponent. So your binary exponent value, you have 5 minus 1 equal to 16. What is your 5 here? This is your 5 bits for your n bit for your bias exponent. You can see in terms of the format, bias exponent, how many bits? N bit equal to 5. How many bit for your bias exponent? This one is your floating point. You're going to have 5. That's why you apply your n value represent your bias exponent digit. How many bits you have? You have 5 over here. That's why you apply 5 in terms of n here, minus 1, then you get 16. After that, you need to calculate the EB. EB, you need to still remember the equation. EB equal to bias minus add with your E prime. So what is your E prime? E prime is here. So that's why you will get 15. And all this value, what you need to do, this value 15, you need to convert it into binary. So 15 you will get like 8 plus 4. 8 plus 4 you get 12. 1, 1. Okay, this is 15 in terms of binary. So if 15 already over here, you will get like 1, 1, 1, 1. You get 0 here. And your value for here, you will get 1. And the rest will be 0. So easy, right? For this example number 19. There is another several exercise 2.5, exercise 2.9, exercise 2.10. So these 3 exercises, please try to do and convert it into the bias exponent. As mentioned in the question, it doesn't mention you a bias exponent because in our starting here, we already asked you that every single example we will use this bias exponent, rather than if we mentioned IEEE, then you need to apply IEEE, which is you still not yet learn. Okay, that is on your bias and also floating point using your simple model. Later, I will continue with the video for your IEEE 754 floating point standard. There is 2 things, which is you need to remember the format for single precision 32-bit and double precision 64-bit. But I will continue with a different video because it took too long now. Maybe it's going to be good for you to take a rest, right? So meet you again in a next video. Please do all this exercise before you move to the next video. Okay, bye bye.